We are going to look at discussion 2 using an IFF, which is initial force diagram, final chart, and impulse to change momentum. So first what we want to do is draw our initial and final sketches as written from the problem. Okay, so we're going to draw our 1,000 kilogram car that is going into the barrier, and it's traveling into the barrier at 30 meters per second. So we're going to just draw, here's 1,000 kilograms, and this is where I'm going to say 30 is. So now remember that the area is the momentum. So this will be for before the crash, and then during the crash we're going to draw during the crash. So here's the car as soon as it hits the barrier and it's making the crash. So, and then after the crash it's still in the barrier, but maybe it's more crumpled. Okay, and it still has a mass of 1,000 kilograms, and at this point the velocity is 0 because it goes from 30 meters per second to rest. So there's no speed at that point. The question is asking, at what force did the barrier apply to the car? So it wants to know what the force was at this point right here. Now it happened for 2 seconds, and we don't know what the force is, so we're going to use algebra to solve it. So our initial of 1,000 kilograms times 30 meters per second plus some unknown force times 2 seconds is going to equal our mass of 1,000 kilograms times a velocity of 0 meters per second. And so here 1,000 times 30 is going to give us 30,000 kilograms times meters per second plus a force times 2 seconds is equal to 1,000 times 0 is going to be 0 kilograms times meters per second. So by doing algebra, we're going to subtract 30,000 from both sides of the equal sign. And we have the force of, not force is equal to, unknown force times 2 seconds is going to equal to negative 30,000 kilograms times meters per second. And we divide by 2 on both sides to cancel it out. And we get force is equal to negative 15,000 newtons. So our final force is 15,000 newtons, but we know that it is going to be not necessarily negative, but it is 15,000 applied onto the car. So this 5,000 newton of force, to avoid damage to your car, we want to take 15,000 and we're going to decrease it to 5,000. And so that means that it's going to be multiplied by 1/3. So to change this, we're going to decrease our force by 1/3. Our mass stays the same. The time of the crash we can't really change right now, or I guess we can, but there's two things. So if we don't change the time of the crash, then what we can do is decrease the change in velocity. So the change in velocity is going to be what we started off with at 30 meters per second coming to rest, and so our change in velocity is 30. Okay, so we can decrease that by a third. And we'll get 10 meters per second. Now, let's say we don't change the velocity and we keep the velocity the same. So now, what we can do is we keep this the same. So the velocity is still going to be 30. But what we can do is increase the time by 3. So what that will look like is we increase it by 2 seconds, and if we increase the time of the crash to 6 seconds, then that will decrease the that will make it safer, right? But so that means we'd have to increase the crumple zone or reduce the change of speed. So that means our initial speed would need to change to 10.